This is the Introduction to Quantum Mechanics by Griffiths. This is a very common first textbook for a quantum mechanics class, and we're going to be going over it in very simple detail, attempting to explain it all from very simple, basic physics concepts. So starting from the beginning, our very first section is 1.1, and this is the wave function. So if we had some particle or something, and it is in motion along one axis, then it's going to have a force. A force is what caused the motion. So to begin with, our person, who has some mass to them, so they have a mass m. They started out not moving, so their velocity was 0. Then they started moving, and their velocity was something that is not 0. That means that the velocity changed. So the velocity v changed from 0 to some other number. Their position in one dimension we can say is x. If they started out here at x equal to 0 and they ended up here at x equals not 0, then they changed in position. So what we have here is that our velocity means that you changed your position over some time. So I could write that as being a change in position over a change in time. If you started out not moving and then started moving, then that means the velocity changed from 0 to something that wasn't 0. And we can call that the acceleration. So our acceleration is our change in velocity over our change in time. If I were to write this as a graph, and I had just some position and some time, and then I had a change in position over change in time. My position is changing, my time is changing. Then the slope of that is going to be the velocity. I could do the same for the acceleration graph. So for acceleration, I could have velocity and time. And if my velocity is changing and my time is changing, then the slope of that is going to be the acceleration. If I have more than one variable that my value is a function of, then it might be a little bit more correct to use the sort of notation that we see in the very first page of Griffiths here, which is instead of a regular d, we use del, and that's to indicate that it is a partial derivative. So this would be a full derivative, change in something over change in a variable, change in something over change in variable. This is saying specifically that it's a change in this specific variable over this specific variable. So I could have something moving in 2 dimensions, or I could have something moving in space and in time. So I want to be specific about which ones I mean here. Now whenever we define something that's moving along an axis like this, we say that the force is what caused the motion. So the force is what took something that has mass from being at rest, say, an object at rest tends to stay at rest unless it's acted upon by an outside force. That force is defined as being the mass times the acceleration. We can't have something that's moving without an acceleration. We could have something that has a constant velocity. So our velocity versus time graph, we could have it be constant, but we can't have something go from rest to go to motion without there being the application of a force. And this is what we use for anything that has mass, and this is in the classical sense. So this is classical motion. Another way to look at classical motion would be to think of the potential energy. And our potential energy is going to be a force times a distance. So if I have something that has a mass m, and I lift it up to some height x above the floor, and then I drop it, it's going to hit the floor with energy equal to the force of gravity times that distance x. The higher I lift it up, the more energy it's going to hit the floor with. I can drop an egg from a distance of 1 inch and I probably won't break the egg. It won't have enough energy. I can hold the egg up to a distance of 3 feet and that'll probably be enough distance to break the egg. So force equals distance times force equals potential energy. Let's look here. So I can divide both sides by x, and I see that my force is my potential energy divided by my distance, or I could write that as my change in energy over my change in distance. If I was going to graph, let's say, the force, so we have our potential energy and we have our distance. The bigger I make the distance, the bigger the energy is going to be. So I make a graph that looks like that. The slope of that is force. That means that force is the derivative of potential energy with respect to distance x. Now we already determined that velocity is the derivative of the position with respect to time. Acceleration is the derivative of the velocity with respect to time, meaning that I could also substitute in this expression for this v here, and what I get is that acceleration is the second derivative with respect to time. If I were to draw that out as a graph, let's say I have something, we'll say it's falling like that. I dropped my person or my egg. At this point, the slope is 0. And we can see here the slope is changing until it becomes very steep at the end. So if I wanted to draw that as a velocity graph, that means that I will just draw the red slope part. So it starts at 0 here. Let's actually bring this axis up here. Because we have negative numbers. So it starts at 0. Here it's a negative slope, and it's not very big. A negative slope that's a little bit bigger. A negative slope that's bigger, until a negative slope that's fairly large. And my velocity ends up being a straight line. And the slope is the acceleration. So my acceleration is the slope of the slope. If I have a curve like this happens to be the way that something would fall on Earth. So this would be like x is proportional to t squared. My slope of that gives me a velocity that's proportional to t. It gives me a straight line. That's how things fall towards Earth. If I let something go for some height, it's always going to follow this sort of trajectory because the acceleration due to gravity on the Earth is a constant. Quantum mechanics starts from a completely different point of view. So instead of having F equals ma be the equation by which we can define the position of anything, this equation tells us everything we need to know about a particle moving in classical motion. I could go ahead and rewrite that in a little bit fancier terms and say that the force is the derivative of the potential energy with respect to the distance equals the mass times the second derivative of the position with respect to time. So I see that my first derivative with respect to distance is proportional to my second derivative with respect to time. If I know something about the force, I know a lot about its position. When we want to solve a problem with quantum mechanics, however, we now have to consider something else. Instead of supposing that something is going to move upon a trajectory that's defined by these relationships, we have to assume everything is a wave. So everything is a wave, meaning that it's going to follow wave mechanics. So for a wave, if I have some position, I can graph a position with respect to time. I can start at 0 position, up to some magnitude, down, up again, and then down. So I will have some change in position with respect to time, like say a planet orbiting around the sun. It starts here, after 90 degrees it goes here, 90 degrees again it's over here, 90 degrees again it's back here, and then it goes back again. All I do is just flip that on its side and I get a wave. I'm going to use a sine wave because I'm going to decide that it started at 0. And what we're assuming in this equation here is that everything's going to follow these mechanics. The most important part of these mechanics is looking at the derivative. So here, at this point, my derivative is very steep and it's positive. At this point here, my derivative is 0. At this point here, my derivative is very steep and it's negative. At this point here, it's 0. And at this point here, it's very steep and it's positive. And then it's 0 over here. So if I graph that out, what I get is another wave, but it's just shifted over. So I get a cosine wave. So my derivative of a sine wave is a cosine. If I take the derivative again, I see that my derivative here is 0. My derivative here is very steep and it's negative. My derivative here is 0. My derivative here is very steep and it's positive. And my derivative at this point is 0. So what I get for my second derivative is a negative sine wave. So my velocity is the derivative of my position with respect to time, and my acceleration is my second derivative, but it is equal now to the negative of the first graph. So what I have for a wave is that for any position x, if I take the second derivative of that with respect to time, then I am just going to get the negative of what my original position was. I can do the same thing here, considering graphing it as a function of space instead of as a function of time. So I can consider something like a planet rotating around the sun. After every 2 pi radians, or every circumference, it's going to be back at the same position again. So my position also follows the same exact trend. If this was 0, this would be fairly far away from 0 in the positive direction. This would be 0 again, and then we would have far away from 0 in the negative direction now, and then now it's back to 0 again. So the position is also periodic, meaning that if I do the same trick again, I get my derivative of my position in terms of position. So I take the derivative with respect to space now, and I get the same thing. I get a cosine wave, same as I got with time. And then if I take the derivative again of that, I will get the negative of the position. So that means that with respect to time, some wave is going to have where the second derivative with respect to space is just going to be equal to the negative of this function. So I'm just going to call it u. So here, let's call this one u as well. I have that the second derivative with respect to time equals negative u, Over here, I have that the second derivative with respect to position is negative u. Now, to be exact here, we are going to have a couple of factors come out here if we use a real system. And that's going to be some constant that we'll just call c is going to come out in front there. And that's going to be due to the nature of when we take a derivative. So we're going to call that one x. Okay. I wrote that one upside down. That's going to be just some constant c squared. That comes from if I have, say, my u, and that's going to equal, say, sine, and then we have some, we're just going to call it k, x. If I take the derivative of that, du dx, then that's going to be cosine kx, but I have to take the derivative of the inside times the derivative of the outside. So I get a factor of k out. I take that derivative again. I will get the derivative of the inside k times k times the derivative of the outside, which is now going to be a negative sine kx. So once we start considering something a little bit real, we have to consider the right unit, and that means that we have this constant come out of c squared. So because everything's a wave, everything has to follow this equation. There's no way around that. In this right here, our very first equation in quantum mechanics, the Schrodinger equation, that is going to just be assuming that everything that we know about the particle can be determined by something with a wave function. The wave function has to be a wave that satisfies the earlier equation, and that wave function is going to tell us everything we need to know about the particle. Here, that wave function is going to be called psi. The wave function is going to be limited to something that satisfies these conditions. There are also a few other limitations on the wave function. Since the wave function tells us everything we know about the particle, then we are limited to things like a probability of finding the particle. The particle has to be somewhere. The reason this leads to what we would call quantum mechanics is that once we have something in a wave form, now we have limitations on it. So here, instead of having any potential energy be possible, we now have finite possibilities for these potentials or for these wave functions to satisfy this equation. So in order to find the wave function, we can apply the Schrodinger equation here. And then we have to consider all these other factors to be constrained by the wave function. So our positions, x, are going to be constrained by this guy being a wave. Our allowed energy levels are going to be constrained by it being a wave. So let's look at a little bit more detail of this guy. And I can go into more detail about where this comes from, though it is not a direct derivation. It's more of plugging in an example and seeing how that works. So here we have Planck's constant. This comes from Planck's experiment of looking at energies of light spectrum. And this would be the smallest step in energy possible with an increase in frequency. So our units here are joule seconds. If we have energy of light, that is equal to h bar times omega, where omega is the angular frequency. So for each 1 omega step up, we get 1 h bar increase in energy. I increase omega another angular frequency unit up, another hertz up. I increase the energy to 2 h bar, and it makes a line. So my energy versus omega graph has a constant slope, and that is equal to h bar. I is just the square root of -1. This is something that comes out when we consider our plane wave solutions to these problems. So our most generalized way of writing a wave is to consider some psi equals psi naught, and then e to the, we will have space and we will have time in there too. So this is our most generalized form of a wave. Now we have our wave function. So that has to be some function that satisfies a wave equation. The wave function is going to be different for different types of systems. We are going to use this equation to solve for the wave function. And then the time derivative of that wave function. So the derivative of that wave function with respect to time times IH bar, both constants, is going to be equal to h bar squared over 2 times the mass of the particle times the second derivative of our wave function with respect to space or position. So that's our position, plus the potential energy times the wave function again. Wave function. So instead of having F equals ma be our defining equation, being the equation that we can use to find out everything we want to know about the particle. Now it's the Schrodinger equation. Now it's this guy. This tells us everything that we could ever possibly want to know about the particle will be wrapped up in the wave equation. Which you may wonder, well, if that equation tells us everything we could ever possibly need to know about a particle, then why is it we don't know everything there is to know about everything? And that's because we don't always know the wave function. And we need to see how the wave function is changing under different conditions. So that's section 1.1 of Griffiths. There's a lot more detail that we could go into, specifically how to get to this equation, how to use an example to get to that equation. In order to get there, it is actually necessary to look at more of the applications of that wave function, how we use that wave function to actually find things. Though there is another paper. This is an English translation of Schrodinger's original paper for how he comes up with the justifications for the wave function. This you can find online fairly easily. You'll notice nowhere in this paper does it actually have this form of the equation. This was also done a lot nicer with more modern mathematics in it. There's an example here that was done by David Ward and Sabine Volkmar about how to get to this equation from looking at energy. So plugging in energy like of a photon from electrodynamics point of view. But for now, that is it on the very first section 1.1 of Griffiths.